Inside everyday air conditioning unit hides a sealed, winding copper maze. When a system stops cooling, technicians face a distinct dilemma. They cannot simply look inside these solid metal pipes to see if fluid is flowing correctly. The entire machine operates as a strict, continuous closed loop. Its only job is to physically absorb heat from inside a building and move it outside. The closed-loop refrigeration cycle relies on four main components: the compressor, condenser, metering device, and evaporator coil. We will focus our attention entirely on the indoor component where cooling happens, the evaporator coil. Because this coil is an opaque, sealed environment, technicians must learn to interpret the thermodynamic data of the refrigerant to determine how the system is performing. Traditionally, technicians attach heavy brass gauges to the machine to read the pressure inside the system, but relying on pressure alone provides an incomplete picture of the cooling process. There is a strict rule of thermodynamics in HVAC. Raw pressure readings are only useful once they are mathematically converted into a specific saturation temperature. By converting pressure to temperature, we can calculate a precise metric that provides a window into the evaporator's efficiency. We call it actual superheat. Calculating actual superheat provides a real-time data point on the fluid's physical state, moving the diagnosis from pressure estimation to a calculation based on physics. The exact moment the refrigerant enters the evaporator coil, it arrives as a low-pressure mixture of liquid and vapor. At the same moment, the indoor blower motor forcefully pushes warm room air directly over the outside of the chilled copper tubing. Inside the pipe, a physical reaction takes place. The liquid refrigerant acts like a sponge, absorbing heat and beginning to boil. This graph plots time against temperature. As long as the refrigerant changes from liquid to gas, called saturation, its temperature remains perfectly stable. Eventually, we reach a critical threshold. The last drop of liquid boils away, leaving 100% pure vapor. That steady boiling phase is what actually cools the room. But tracking what happens after the boiling stops is how a technician checks the health of the machine. With the liquid completely gone, that pure vapor continues to travel through the remaining length of the evaporator coil toward the exit. Because there is no liquid left to boil, any additional warm air blowing over the coil causes the vapor's temperature to rise. This specific temperature increase, the extra heat absorbed after all the liquid is gone, is superheat. The fluid then completes its journey through the indoor unit, leaving the evaporator entirely as a low-pressure, superheated vapor. Calculating the exact degree of superheat tells a technician how much of the evaporator coil is actively boiling liquid versus simply warming empty gas. To diagnose a system, we first establish a mathematical baseline called target superheat. For a balanced system, this target usually sits between 8 and 20 degrees Fahrenheit. By calculating the machine's actual superheat and comparing it against this target, technicians can identify hidden imbalances. The first failure state occurs when the actual superheat calculation is significantly higher than the target. Diagnostic tone. Physically, this means the liquid boiled away far too early in its journey. The majority of the coil is left filled with gas that is no longer effectively absorbing heat. This is a starved evaporator. A starved evaporator indicates the system is either drastically undercharged with refrigerant or a physical blockage is restricting the supply to the coil. We must also check for the opposite scenario, where the actual superheat falls below the target baseline. This presents a risk to the hardware. A low superheat means the warm indoor air is failing to boil the liquid fast enough, pushing raw liquid toward the coil's exit and the compressor inlet. This condition is known as an overfed or flooded evaporator. Flooding is typically triggered by restricted indoor airflow, an overcharged system, or an overfeeding metering device. By tracking the physics of the phase change, a technician can see exactly where the liquid ends and the vapor begins, providing the data needed to pinpoint why a system is failing to cool.